Welcome to the Operations Science Podcast, where the art and science of operational excellence come to life through captivating stories of triumph, challenge, and transformation from the front lines of industry. Our distinguished guests, from manufacturing pioneers and medical device innovators to aerospace visionaries, diagnostic lab leaders, and major capital project leaders, unveil the hidden patterns and powerful insights that drive exceptional results in the complex world of operations. Join us on this journey of discovery as we explore the brilliant minds behind the systems that make our world work and uncover the leadership secrets that could revolutionize your approach to operations forever. Here is your host, Ed Pound.
Welcome to the Operations Science Podcast. On this episode, we explore how a single entrenched operating habit put billions of dollars of semiconductor revenue at risk, and how applying operations science provided a new lens for understanding and fixing performance. That shift in perspective not only safeguarded a critical product launch, but cut cycle time by roughly 80% in one of the most complex manufacturing environments in existence, semiconductor manufacturing. Our guest spent decades in semiconductor manufacturing, from running day-to-day fab operations to leading a high-stakes turnaround to support a critical new product launch of a new chipset. Along the way, he helped transform a factory from a fat fab with excess WIP, constant reprioritization, and hidden problems into a trim fab that produced steady shipments, predictable output, faster flow, and dramatically shorter cycle times. Now retired, he brings the clarity of hindsight. His frontline lessons, however, remain highly relevant today because operations science is universal and timeless across semiconductor fabs and virtually any production system. Please welcome to the Operations Science Podcast, Zane Rakes. Hey, Zane, how you doing?
Good, Ed. How are you?
Good. It's good to catch up with you again. I'm really looking forward to this episode. To give the audience a little bit of background, I met Zane, I think back in 2004. I was working for Factory Physics, Inc. at the time. He was at Intel, and we accomplished a lot of good things there, which Zane is going to elaborate on. You will hear Zane talking about Factory Physics. At the time, it was called Factory Physics. That's where Operations Science sprang out of. We rebranded it as Operations Science because what we found was it applied everywhere. It wasn't just manufacturing. We worked in hospitals, very large construction projects, project management, aviation maintenance, repair, and overhaul. So you might hear the interchangeable Factory Physics and Operations Science. Just think of those interchangeably. All right, Zane. So if you would start off by letting the audience know a little bit of your background, how we got started at Intel.
Okay. So I started at Intel in the very beginning of 1992. And I came in as my first job, which was short-lived, and I'll explain why, but it was called a equipment engineering supervisor. And it was called the EES org, and we ran the maintenance technicians that did all the maintenance work in the factory. But at that time, Intel was blurring the line between the operations work and the equipment work or the maintenance work. And so I started there. That job quickly morphed into, we started separating it again, and we morphed into a more traditional operations management type role. And from there, I kind of just worked my way up through the manufacturing ranks at Intel, through supervision into shift management, did a couple of other jobs working in as part of the manufacturing staff, and then moved into a factory production manager, that's where I met you. I was a factory production manager when I met you.
Yeah. Talk about a little bit how that all got kicked off. It sounded like you were a little bit reluctant at the beginning, as many people are.
Yeah. So as I said, I was the fab production manager, and as part of that, we ran kind of the tactical operations across. We had 4 shifts. It was a 7x24 structure, and we were responsible for managing the day-to-day operations of the factory. Now, there were teams that worked within the factory that had shift management and their own managers, but I kind of provided the overall direction and tactical management as part of that. And and spent a lot of time, I was the interface between the manufacturing manager and the production teams at the time. And I also had what was called the operations systems engineers, and they reported into me, and we managed all the way from like MES upgrades to all of our tools and systems that we used in the factory to manage with.
Were you guys doing capacity planning, longer range capacity planning, or just managing day to day?
No, we didn't. We had a separate IE group that did the capacity planning, but we worked very closely with them. They were probably, I'd say, the right hand and the left hand of the fab and stuff. So we worked together very closely. And I can talk a little bit more about that later. But so when I got pulled in by the manufacturing manager one day and said, "Hey, we're bringing a group in to help us kind of understand how we can maybe run the factory a little bit better. It's the factory physics group, and you're going to be one of the key contacts for them and stuff." There were other key contacts as well, but I was one of them, and I was just like, "Oh, I got so much to do," and it just seemed like it was just such a big distraction. It was like another consultant coming in, and so anyway, got into it, and met you and Mark Spearman and your team that you brought in, and I don't know how long it took, but suddenly I was starting to realize, like, wow, this is very eye-opening to there's a different world out there about how a factory could run. And I learned something early on from you guys because you guys kept talking about what was the ideal state versus we were always benchmarking. We were benchmarking the guy down the road and stuff. And you guys talked a lot about things that we just never thought about. And also the thing I learned very quickly was how variability was impacting our factory. And now we had terms for it. And one of the things that we used to talk about, I had one of my peers that worked very closely with named Eric Stebbins, when we used to talk about bear traps. It seemed like inventory would move from one bear trap to the other. You get stuck in a bear trap that's there for 3 or 4 days and we can't get it out. And then finally we get it out only to move into an operation that had no whip. But it turns out it's another bear trap. And it just kept happening and happening and happening. And so we spent all of our time kind of managing bear trap to bear trap was the term that we used back then. And, but factory physics started bringing another way to look at things. And I started realizing the true, I call it the corrupting influence of variability and how that just so degraded our factory. And as part of that, I think as a production manager, we're kind of trained like, oh, the doggone tool is not up. Why isn't the tool up and running? Why isn't the tool up and running? And the other thing this exposed to me was the fact there's many other sources of variability and not just the tool being down. But that was kind of always the common thing that we were talking about.
Were you guys, did you have specific calculations for variability, or was it just the effect that you saw and you're always wondering about the cause and how to get better?
Yeah, we were always we didn't really calculate variability across understanding the coefficient of variability, any of that. We did not do that kind of work. And so it was just this intuitive, like, okay, here we are again. We're back in another bear trap.
So we came in, I think the engagement was basically to help improve cycle time, if I recall. And that consisted of, as you mentioned, doing the training and then doing some analysis, you guys pinpointing some areas. And then that was it. I mean, we left you on your own after you had gotten the concepts, and I think you were incorporating it into your lean program. So a couple of things. One, talk about that, how you incorporated the concepts into your efforts. But really what I want you to share with the audience today is your experience at Fab 23. So if you would just elaborate and then make that transition, please.
Okay. So not long after when you guys left, and it was very early in 2005. I was asked if I would go up to the Fab 23 up in Colorado Springs. They were having some real hard operational issues. They were behind on their output and they needed some help. And so they asked if I would go up there and just take a look and see if we could help them. So I went up and quickly realized that their MES was out of date. A lot of their whip management tools were not up to speed. Because, running a factory with thousands and thousands of wafers, you have to build, there's traceability issue. You have to know exactly where everything is at any given time, what products are where. And they were just hadn't updated their systems, and yet the world around them had gotten more complex. But at the same time, they were going very aggressively down the lean path, and they called it manufacturing excellence. And so anyway, we spent some time up there. I brought my systems engineers up there. We did a very rapid upgrading of all their tools. It took us about a week. We're working very long days.
Well, are the tools, you mean the MES or
The MES, yeah, the factory tools, all their WIP management tools, their product scheduling tools, and also some of the MES functions were there. And so we worked closely with the automation group, and we got all those tools up on current configurations and loaded with the right configs.
I'm sorry. MES, Manufacturing Execution System, which is a data repository for production data that you guys use to run the factory. Yep. Sorry, just want to make that clear. Yep.
Yes, yeah, with the heart of the factory in the sense, yeah. And we upgraded that, and then it wasn't long. It was right. We're kind of doing our final report out to the factory staff about what we had done, and the factory manager pulled me aside and was talking to me about it, and he goes, "Hey, we're getting ready to hire a new manufacturing manager. If you're interested, really like you to put in."
What were the results of your initial analysis that you conveyed to the manufacturing manager?
Their product schedules were actually worse than they thought. Was the first thing, that they were grossly over inventory. They were running about 100 to 110 day cycle time. And the key products that they needed to get out, they were in the middle of transitioning. There was a new product that Intel was bringing into this factory only. It was a chipset that was going to support the latest and greatest microprocessor. So we were a 1-to-1 attach rate. That factory was going to be a 1-to-1 attach rate to the new microprocessor. And it was probably had somewhere in the neighborhood of $14 to $15 billion of revenue at risk. So we needed to get that right.
Okay, I'm sorry. Another clarification. I'm just thinking about what people understand in their context as they're listening to this. So you guys, at the times of 20 years ago, the technology was 200 millimeter wafers, right? And nowadays it's 300. I don't know if they're larger or not, but they've gotten a lot bigger with a lot more steps in the process, a lot more microprocessors on each wafer. And how many steps were in your process?
So the typical 200 millimeter processes back then, I think we were running between about 700 to 800 overall steps. And then within that, there was about typically 120 to 150 that were considered to be, we called them activities, or where value was added to the wafer and stuff. It was a true transformational, where we actually transformed the wafer, as part of making the microprocessor. A lot of the other steps were basically defining a transistor, putting photoresist down, stripping the photoresist, etching it, diffusing, things like that. So,
okay. So I'm sorry. So I cut across you there, but thanks for the clarification. So you talk to the manufacturing manager, you say, you think you're in trouble. You really don't know how much trouble you're in. The cycle times were 100 days. And that's where I cut across you. So,
yeah. Yeah. So they were needing to kind of get this inventory out, these products out of the factory, so they could start transitioning. And there's some process changes. New equipment was coming in, but we needed to deal with the current production load to make that transition successful and be able to ramp the new product and get it up to satisfactory levels. And so that's what we were doing at the time. And they were greatly behind schedule on the old products, which was putting the new product schedules at risk.
So you took the job as manufacturing manager. Talk a little bit about, coming into that, and now your appreciation, a different look at it from the factory physics standpoint, and where it went from there.
Okay. So basically I moved my whole family up to Colorado. We were living in New Mexico at the time. And so we got there and we immediately started working on, okay, how do we get the factory stable? And at the same time, I was trying to understand, I'm new in this factory. I'm trying to build relationships, trying to become part of the organization and the factory staff, and understanding the team that I had. Fab 23 had just under 2,000 employees at the time. And my organization was pretty big. As part of that, I had about half of it. And stuff. And we were kind of a traditionally set up factory. But as I came in, we started having some very rich conversations at the factory staff level. And it was about, what do we need to do to transform this factory? Not just really just do the kind of the constant day-to-day improvement, but how do we transform this factory over time? And they were already well into a lean program there. And so we had a great foundation to pull on. They also were working on a very strong maintenance program at the time. And so I think the piece I brought into it was the factory physics And so we started talking about it. I was bringing in the concept of one, our high whip situation was going to forever be a problem until we dealt with it. And traditionally, Intel factories they were rated when they built a new factory at Intel, or we retooled the factory. It was always done with how many wafer starts per week could we run into the factory. And so that's how we rated the factory. And so factories were typically measured. A factory manager would, if they had to cut their starts, it was a phone call to the highest levels of Intel manufacturing, at the corporate level, and it was a big deal that we had to cut starts. Nobody ever hardly asked about the fact that we didn't hit our output the week before or the week before that. But if you cut your starts, it was a big deal. So wafer starts per week was the mantra of the Intel manufacturing. And that's what I learned coming up through the ranks. And, the saying is that you can't ship a wafer you never started.
Right. Yeah. They didn't look at no consideration of the state of the factory. And that actually is common. I mean, I've worked with other semiconductor manufacturers, and that for some reason in semiconductor, that is a prevalent mindset.
Yeah. You have to keep introducing wafers, and you shipped 5,000 last week, but you introduced 7,000 this week. And why is my factory so over inventory? And you keep doing that month over month over month, and it gets to be a pretty big problem. And, and then there's always this, when a product line is transitioning out, there's always some runway at the end, and they clean it out, and everybody breathes a big sigh of relief, but it just happens over again with the next product coming in. So it was a very frustrating behavior to me after I started learning about that we could do something different about the factory. And so I brought that to the table on the factory staff. So I think with our lean program, our equipment excellence program, and then bringing factory physics over the top of that, I think we were able to really start transforming the factory. But we started transforming the organization first. We started really focusing on what do we need to do to get our teams really on board with this. And one of the engineering managers and one of our HR people had been talking about types of work. And we end up settling into breaking our work into operations work, into equipment maintenance work, and then process engineering work. And we divided our teams up accordingly. So that means we had to shift resources between groups. And what that did was it really allowed us to get excellent in every area, was the goal of that program. So we got very dedicated about how we did that. We had a lot of jobs that were called single job family, that a lot of different jobs we encapsulated within one job, and people were expected to know a little bit of everything. And we wanted to build a deep silo that went deep, and people had a rich understanding of their work, all the way down from the most junior technician in the factory running the equipment, all the way up to the process engineer understanding their process center. And so we started unboring those lines and really getting a dedicated focus on that. And we considered that to be one of our primary, it was a must do for us. And we quickly did that. When we had high agreement, the factory staff was small, and we were all greatly aligned, and we're going to go do this. And we made that work.
All right. Good deal. So you are there, you've done assessment. It sounds like you have the fundamentals. The operations science gives you a different lens on what you're doing. And one of the things it pointed to was the importance of whip control, tying that to the performance of the factory, not the start schedule. And how did that discussion go over with the group, particularly the fab manager, who's the guy who has to make the call to say we're going to moderate starts?
Yeah. So the initial reaction, because obviously we had a fab planning manager that was there at the factory. They actually reported into a different organization outside of the fab, but their job was there to basically bring all the product plans in, and they controlled the weekly starts, the product mixes, things like that. And also, somewhat the product priorities within the factory. And as part of that, I was thinking about, we cannot be successful if we're going to continue to start wafers in an over inventory situation. We cannot really achieve the things that the factory really wanted to do. And we're working hard to transform the organization. But at the same time, I started bringing in the conversation around, we have to be able to control inventory, and we have to be able to get our inventory down if we want to run fast cycle times. That meant we had to get inventory out of the factory, but we just could not keep pushing wafers in and then they sit stagnant. And along the way, we started learning, started having this conversation. And the factory manager, he went through an advanced program at MIT. Very smart guy. He was one of what they call Intel's leaders for manufacturing, and he had a really good reputation across Intel, a lot of good influence. And he started running interference for us at the Intel top of Intel manufacturing ranks within our Intel VPs, and really getting some buy-in that we could start doing things differently. Since we were going to be sole source for this product, they were open to letting him do things because he had such a good reputation.
But where did his epiphany come that, oh, maybe that's something different? It sounds like you worked a little persuasion on him.
We did. And part of that was we started talking about, I'll just use Little's Law as an example and stuff. And Little's Law was a very a simple mathematical equation that just shows you if I have this much inventory and you want to run this type of cycle time, this is what has to happen. And we cannot do that. That is just outside, that's 30-40% more capacity than we have if we're going to do that, to run that type of cycle time. And so and he was very data driven. And so we started building graphs and some simple presentations to show if we want to run the factory at this rate, this is what we got to start looking at doing. And as part of that, he was asking questions and he said, so how do you propose to do that? And so we started proposing that we needed to come up with a way to control starts into the factory. Doesn't mean that we don't start wafers, but do I need to start 5,000 every week, or can I start at a reduced rate and get the right products in? And we really try to manage inventory out the back end of the factory. And so we're in the midst of getting all this old inventory out of the factory, and we're getting out through just, it was just very hands-on, very 7x24, very hard, just your grind, but was the norm for Intel manufacturing, and probably most fab at some point. But we knew there was a better way, and a better way to use our people, because it just burns everybody out and it just isn't fun. And so showing that there was a better way to do it. And then when you start comparing your actual cycle time compared to your theoretical cycle time, and you start looking at the gap, and our theoretical cycle time for one lot of 25 wafers to start at the beginning of the line and go all the way through the line was about 16, 17 days. I don't remember the exact number, but it's about 16, 17 days. And yet we're running 100 to 110 days consistently. A good week is if we broke under 100 and stuff. And so how do we go off and reduce that? And understanding that the main issues were variability and the corrupting influence of variability across our factory. And we were just a typical Intel factory. We had what we called bear traps back in Fab 11. It was the same type of situation. And what we were always like tactically managing inventory out of this bear trap, only to go into a process center that had low inventory. And then we find out, oh, this is just another bear trap week over week, that something come up to bite us. And then we're starting to understand, this is one of the key learnings I learned when you guys were at Fab 11, is that variability raises its head in many different aspects. There's process variability, there's equipment variability, there's human variability. And within that, there's a lot of our human processes were sources of variability, or sources of things that just kept us from being able to effectively run inventory through a process center. And so as we started approaching that, and that's what gave us that types of work. Now the types of work model started coming into play. And so we were, as part of our lean journey, we were actually going down and doing a lot of direct observation on the floor. The factory manager would go with us. And you want to see something embarrassing is when you take your factory manager out and you're showing them one of your prime, you got our brand new litho scanners, these laser scanners that are running, and there's 8 or 10 of them in there, and 4 of them are sitting idle, waiting for data from some analytical place, from an analytical operation. And so we started looking at that because we had to run a send ahead to qualify every time a new product came in and we did a setup change, we had to run a send ahead to ensure that all of our parameters were ready to go on the scanner.
So there's another clarification. So a send ahead is basically what the engineers say is you can't run anything else. We have to run these wafers through to qualify the process through this certain number of steps. Is that right?
Yes, you had to run it through. So basically we'd run like a 6 wafer, 10 wafer send ahead, and it would go through that entire litho loop. And we get to the analytical step where they could read the critical dimensions and various other aspects of that. And then we'd say, okay, that process is good, or we need to make a quick adjustment to the tool. And then we'd have to run another send ahead through it. And send aheads were taking, on average, somewhere between 3 to 6 hours to go through that loop. The raw process time was actually very short, 45 minutes or so, to get it to the analytical step that was required. Yet there was all this queue time, and it would just get buried. And this is another one of the things where inventory hides problems, right? And so I have a sit ahead that gets buried behind all this other inventory. It's at a simple operation, like the wafer's getting ashed or the wafer's sitting there waiting to be read at the analytical tool. But there's other priorities in process. They didn't know the send ahead was coming. They didn't, whatever the thing is, but the inventory is hiding that problem. And the fact that I need that turnaround on that data quickly, because I have a very expensive tool sitting idle, waiting for that data. And I may have to go off and make adjustments to it and do the same process again. So as part of that, the factory manager got to see this for himself. It was embarrassing the first time we did it, but actually he was very graceful, and he was also like, okay, now how do we fix this? What do we need to do? And he was really good. And I learned this from an example of him, because he was really strong on the lean side. And we started using, that direct observation, and how do we have the conversations with the engineers and the technicians on the spot, and start quickly sometimes we call them temporary countermeasures. We put a temporary countermeasure in, and as we worked on making the process better. And we got our send ahead process down to where it was occurring in under an hour. And tools were sitting idle. So that was one of the ways we're getting process centers to start producing at the required rate. And because your scanners are always going to be one of your constraint tools.
So it sounds like, and actually, I think we coined this term when we met you at Fab 11. It's that strategy, which is so common in semiconductor, we call the fat fab strategy. You just stuff the fab with whip, and the guys at the end, the planners, it's like at a smorgasbord, all you can eat, right? They just take out stuff at the end of the week. And so, as a matter of fact, if they're looking at the predictability of what they're going to ship at the end of the week, it should be pretty easy because there's so much to choose from. They can just take whatever they need. But you were talking about now going to the trim or the skinny fab. Hopefully it's trim because it's in shape, not skinny because it's starved. The trim fab. And one of the things that occurs is it's a rough transition, because you tell people, the fab manager's telling all the people, like, we're going to start moderating starts. We're going to do so whip, and things are going to get better. But what happens is the dynamics are, when you have a fat fab, you just pull out whatever, and you can just, stuff yourself with whatever you want to ship. With the skinny fab, what happens is, it's trim, and so you're getting stuff through right to schedule, and it's flying through the fab, relatively speaking. But there's this transition time where the people in planning, now you've taken away their all-you-can-eat privileges, so to speak, at the smorgasbord. And you haven't yet gotten to where you're shipping stuff through the fab very quickly to schedule. That's a rough transition. How did you guys manage that? I mean, what were some of the things you saw, and how did you finesse that?
Okay, so the we had the air cover of the factory manager on the start side. So we started putting in, and I can talk more about this at some point, but this how we did our starts, we call it our starts protocol, and how we manage starts coming into the factory based on factory output. And there were some different vectors that we would look at. But the other part of it is so every week, planning is, like you said, they want this big smorgasbord. And we started forcing trade-off discussions. We're going to ship this much this week, and you want us to prioritize this product and this product, but we can't do that. And so we started forcing conversations around how much inventory is downstream of us, how much inventory does assembly test have. And as you look at that, many times assembly test had big buffers, but the planning teams never wanted they wanted to always keep that buffer big and not ever allow the fab, the fab planning folks never wanted the fab to be pointed at saying they didn't deliver and stuff, even though we were under delivering every week, but we were always managing these product mixes and pulling stuff forward and letting other stuff sit. And so we started forcing trade-off conversations. I'll give you this many hot lots this week. You pick which ones you want, but what are you going to give me in return? What are you going to give me back? I will not run more than this at a priority rate for you because it's going to impact the rest of the tool sets. Because when we ran a priority lot through the factory, tool sets were required within a certain window to break their setup, get that product on and move. Some places it was not a big deal. Other places like lithography, it was a big deal because they're product specific. And so forcing those conversations and those trade-offs with the planning teams became our root cause as we were trying to get some, we needed to get traction on getting inventory out of the factory, all inventory out of the factory, not just these priority products for them all the time. So we gave them a very limited set that they could pull each week.
So I mean, well, so that's interesting because you mentioned that the planning group reported up through a different organization than the fab manager. So was it the case that the fab manager just said, you're going to do this? Or did you have to have discussions with that overall organization? How did that work?
For myself, I did it more at the local level with the fab planning manager. But the factory manager, he actually took that up higher and got buy-in across the board. Now, I'm not going to say it was a pleasant conversation with the planning group, but it was one that actually he had the reputation and the influence that he was able to pull that off.
Yeah. Well, that's one of the things I tell people when they're having these conversations is there are things that you should be passionate about and you should be, maybe pounding on the table about. What happens is people sometimes are just pounding on the table about anything like, oh, we need to make starts. Well, really, do you need to make starts? And so, the fact that you have hard conversations, at least you've got data and, you have the basic science that says, look, this is what's going to happen. It's predictable, which tends to make those conversations, like you say, they might not like it, but it's kind of hard to argue with the science.
Yeah, that's true. That's true.
All right. So that was so we're going to do this. We start moderating the starts. Planning is not happy because now they can't have all they can eat, but they work with you. Where to go from there? What kind of things do you see and where did you get to?
The first thing we did is I had a couple of our critical resources that were reporting into me. Was I had 2 industrial engineers that were very strong, and they were kind of self-learners too. I gave each of them a copy of the factory physics book, and we had those conversations. I had another resource was I had an intern from the MIT Leaders for Manufacturing and stuff. And so we were meeting together. We met every morning, and we were working on what we called our starts protocol. So we started really developing that and refining it and building a system. So we would know exactly every week this tool, we were running this process and we were reviewing it every morning to see, does this make sense? Does it not make sense on what we're doing? Based on the last week's output and the current output that we're getting, does it make sense for us to start this many wafers? Does it make sense to start this mix of wafers? Things like that. And so we continued, and those 2 IEs continued to refine that system. And it was a giant Excel spreadsheet the way it started. We ended up automating it, but it became a very valuable tool in guiding us on how we were going to have this ability to ramp the factory inventory down to what we thought we needed to, and to be able to run. And as we started doing this, we started finding, okay, we're flushing out the old inventory. We have organizational alignment across the board on working on what I say, all the sources of variability. What's the operational sources of variability? Why are tools idle when they should be up and running? Why was preventative maintenance taking longer than expected? Why is this tool down unexpectedly? Availability problems. Why is this process having problems? Why are we having to do all this rework? Things like that. The whole organization was rallied around it. Now, there was also work that the engineers had to do that was preparing us for, long-term, looking a lot of, at the yield data, different things like that. But what we started seeing as the factory started running faster, suddenly we're starting to get our yields parametrically at the back end of the line are starting to get better and better because inventory is spending less time in the factory. And that was one of the key learnings that I had. So when you say high WIP hides problems, and we tend to, the traditional thinking, I think high WIP would hide problems now, but the traditional thinking is that low WIP would hide problems. You didn't know, you weren't testing your tool sets. You didn't know what was going to happen. And we started learning that the first order effect was high whip in the factory. It's in the factory for months. And when you get up to the end of the line, there are inline signals that you missed because that inventory or that whip had been sitting there for so long. And we had some minor issue that we would have retargeted a tool or a process center a little bit differently if we'd known way earlier. So we produced much quicker feedback. And so that was one of the key things that the organization started seeing as well, because everything was getting better. Our cycle times were dropping. I think people's job satisfaction was going up because they were actually feeling they were part of something, that their input all the way down to the lowest level of the organization. When I say the junior technicians in the factory, they were starting to see that their work made a difference. And they had input into like the send ahead process, things like that, and how we could streamline things. So organizationally, you could see that things were coming together, but we started seeing much better end of line data, and inventory is dropping, and the factory just continues to run faster and faster. And then this is where we started bringing in the concept of, wait a minute, what's the ideal state? We know what the benchmark is. We had other Intel factories that had been running faster than us, but now we were junk. But we said, how fast can we go? And what do we need to do? And so we had these weekly product schedules that we needed to ship. And we started getting to where we were 100% to schedule PAS, 100% every week. We started moving that down. We have this new product that's coming through the factory now. And it was a different process node, a little smaller critical dimensions. And but we were starting to hit our schedules, and we were actually not having any issues as far as doing that. The starch protocol was working, and it got to a point where over time, starts would equal our output, because that's what the system was designed to do. If our output was, let's say, 5,000 wafers a week, we were bringing in 5,000 wafers a week.
Yeah. Well, I mean, you have some scrap factor, right? Where, some of them drop out because of whatever, but
Yeah, there was some, and there were times where we would say, hey, we need to overstart a little bit. And we also had, which I didn't bring in, we had an engineering allowance for, we would do engineering starts as well every week for engineering experiments and different things. And a lot of times that was production worthy material. And so we could also bring that into our product schedule. So that would help make up if there was a scrap issue. But just in general, we were able to run the factory in a more balanced fashion. But we continued to bring our inventory down, and cycle times continued to drop. And we ended up dropping from the high of about 100 to, like I said, 110 days. And we brought that down, and we were in the low 20s. We were running about a 21 to 22 day cycle time, week over week over week. And stuff. And we did that all the way until we ended life the factory. We did that for well over a year.
wow. Yeah. So the point being there, as you mentioned at the end of the factory, I mean, as all semiconductor does, it's moving to new technologies. And then the life was determined by the move from 200 millimeter to some other, like 300 millimeter or something. Is that what it was?
Yeah, 300 millimeter. Yeah. This was right at that transition when Intel started moving in the transition. So we started end of lifing the 200 millimeter factories. In fact, we were supposed to be one of the first ones shut down, and stuff. And we ended up being the not quite the last one, but we were very close to the last factory that we shut down, because we're running well. Our product was very stable. We had great yields, and so and there was just a lot of key learnings. Like I said, that high whip had so many problems associated with it that we just didn't see at the time. But when we dropped the inventory, we had a high of over 80,000 wafers at some point, and we're dropping that down substantially, like almost less than half. And so inventories in the factory for a much shorter amount of time, less inventories at risk because we're getting fast data turns. And the factory was just running in a much better fashion.
Yeah, that's an awesome story. I'm glad we were able to get you on the podcast to share it, because I think it's basically, like I say, it's timeless. I mean, this same thing goes on now. Now you're to, operations with, 1,500, 2,000 steps, but, the same concepts apply. Along those lines, when you were looking at your ideal state, I mean, the operation science and factory physics basically should give you an idea of what that should be. You don't have to benchmark against somebody else. You can figure out for your particular fab or your particular process where you should be running. Talk a little bit about that.
Yeah, I think the idea that when we look at, I don't remember the exact term in the factory physics book, but we were talking about, high variability versus low variability. And there was a very compelling graph on the influence of that. And I remember that as we started, looking at how the factory could run and what prevented it from running at closer to that ideal state. And we never hit our ideal state, but we're always moving towards it. We weren't moving toward the benchmark. And we continue, we put benchmarks over to the side and we just continue to look at it and looking at, for example, like raw process time. And then what is preventing us from getting closer and closer to our raw process time for a wafer? And now, is that achievable at full wafer starts? No, it's not. But it is definitely something that is there that tells you an idea of, I buy a new sports car and it's supposed to go this fast. Well, does it come close to that? No. And now I got this $1 billion plus sports car and I want to make sure, we're wringing the performance out of it. Yeah. And so factory physics was able to quantify that. I brought the science, I think, into the factory around understanding, I keep bringing up variability, but I can't overstate how much that plays into it across all the way, but also understanding, what can the factory do and what is an operation capable of? And there were times I remember at 511 when you guys were there, you guys were saying, you would tell us, or say, okay, Intel, you're saying that this factory can do this. Our work shows that's not even achievable under these circumstances that you're telling us.
Yeah, sometimes the answer is not what you want to hear, but yeah, it works both ways. Yeah.
Yeah, it does. And, but the other part of it is that I think what people don't understand is that when you start bringing the scientific principles into how you run your factory, that I talked a lot about yield and about how yields were improving, our inventory was dropping, yields were improving, but your cost structure starts dropping as well. And suddenly you start finding you have resources that are available to go off and work on things that you maybe never thought was possible, things that you wanted to do, but you never had time to go do.
If you're chasing wafers, yeah.
Yeah. And instead of we're always chasing problems and we're always, sitting in meetings, and the traditional Intel way was you drag all the engineers in. Why is your tool set not running? And, they feel like they got berated for 30 minutes or an hour. They go out, they come back with another paper plan. It gets shredded and stuff. But instead, we started doing that. One, let's bring the science to it. Let's bring the direct observation piece to it. And let's see, how do we go off and make these operations more efficient? And how do we drive waste out of it? And I learned this from you and Mark, that lean for itself doesn't really make sense. Lean with the purpose of driving out waste that is corrupting your operations is where you need to be focused on.
Yeah, that's a good point. Actually, a lot of times what we find is people think, and industry in general, for decades is conditioned to, oh, what's the latest program? And when we come in, we say, let's start talking about operation science. They go, oh, so we either got to do lean or now we got to start doing operation science. And that's just a completely wrong way to look at it. It makes any lean program stronger, which I think you've said a number of times.
Yeah, it did. And I look at the what I considered to be the backbone was being able to bring the factory physics or the scientific principles into play. And how does operation science overlay everything that we're doing? And then we start bringing in tools to go out and fix the things that we're exposing. And we were really good about, let's direct observation and rewarding people for exposing problems and then fixing problems that made a difference.
Yeah, and they were fixing it, right? You didn't have a consultant coming in there to tell you what to fix. They were fixing it. That's the other thing. When I start working with people and we do the initial training sessions, first thing I say is, I'm not here to tell you what to do. You guys know your job much better than I do. But what we find and what you've seen and described is, without understanding the underlying science controlling your operations, people all get all sideways on things that they shouldn't be really even focused on. But when they understand it, as you have illustrated so well with your story of Fab 23, they turn in focus, and now they're working within a common framework that corresponds exactly to the behavior of their factory, and the results are fantastic.
And I think the other thing that the operation science piece did for us was it forces you to understand not just reality, but what does good really look like? And by being able to put a number to something and to start understanding exactly what good looks like versus what I actually do look like. And I remember just looking at when you guys were calculating coefficient of variability across some of our work process and our work centers. And I was just shocked. It's like, well, no wonder we call this thing a bear trap. We just keep stumbling from one to the next and stuff. And it put that, it quantified it. One of the things I learned along the way is that, okay, understanding that concept helped me identify that, okay, I can use inventory become a proxy for variability. As I start seeing, even when our factory was running really well and we had, low inventory, and I could look at a WIP report, and if I have WIP queuing at a process level, it immediately would flag me just to say, okay, hey, what's going on there? Something maybe that ordinarily, and then almost always you find something happened, something was going on.
Yeah. Now, I will say that is true, that it is a leading, WIP is a leading indicator sometimes. But the thing is, you have to kind of you can't look at, today's WIP problem as necessarily a problem, because there is natural variability in WIP levels. And so WIP go up and down, and
There is. Well, there's an ebb and flow, 100%. Yeah.
there's an ebb and flow, right? But if there's consistently a problem there, yeah, that's something to go look at. All right, last question on this topic. But so we talked a lot about variability. You mentioned calculating coefficients of variation. A lot of times there's the thought like, oh, if I had a perfect way to calculate variability and I could calculate where it was all the time and I could do all these complex calculations, it would tell me exactly what to do. But it sounds like you weren't really worried about that. You were just focusing on the behavior of the system in general. Were you doing these calculations for, coefficients of inter-arrival times and process times? And did that lead you, or describe how that investigation process went?
I think, as part of our starts protocol, I think that one of the things that we did was, and I think our system took into account, we were looking at arrival rates and departure rates and understanding how that would happen within a particular segment of our factory. We're looking early on. And so we made sure that we had a really good understanding. And I think that system had some of that somewhat baked into it. And the IEs that I had and we had another dedicated IE group as well. And we're looking at that type of stuff as well, especially as we're doing capacity. And we had a situation, I think I'd mentioned at one point, that we had one of our laser scanners go down for a very long period of time when one of the vendor reps had made a mistake and the tool was severely damaged and we couldn't use it. And so we had to drive our utilization up. And that type of work became very important for us to understand how are we going to overcome the loss of that capacity, because we weren't going to get a new tool. They cost, millions of dollars. And we knew that the fix was a very long ways away. And we ended up getting to the point where we decided we didn't even need to fix the tool because we were able to wring better performance out of the other tools. But understanding how are we going to prevent this from, because at that time also we were getting into what the Intel processes, we had queue times where wafers could only sit at certain operations for a certain period of time before they would start getting impacted, that we would have, quality issues if they set too long.
Spoilage, like food. Yeah.
Yep, exactly. And so we had to start understanding that and so that type of work become very, very important on how we did that. So yes.
Okay. All right, let's switch to Zane Rakes, the man. So tell me a little bit of background of you. For where'd you grow up? What led you to your career in semiconductor?
I grew up in northern New Mexico, just south of the Colorado border. My parents had a small farm right next to my grandparents' farm, right next to my aunt and uncle's farm, and and it was pretty far out. We were about 9 miles out of town, and we had horses and various other livestock and stuff. And so I spent a lot of my time doing farm work. And my dad actually had a job. He worked for the Fish and Wildlife. And so farming was a part-time job on the side. And, but we spent a lot of time in the outdoors. And we lived right on the river. It's called the Animas River, coming out of Colorado. And so it was pretty good place to grow up. I had a younger brother, and I had two older sisters and an older brother. And but they were my sister was there. She was 5 years older than me, and my older brother was 10 years older than me. And him and I are still very, very close and stuff. He has a ranch up in Colorado, actually. But we spent a lot of time in the outdoors. But my parents had an old like Encyclopedia Britannica or something, and I used to sit. We didn't do a lot of TV, but I used to sit and read those things all the time, and it really got me interested in technology. So
Yeah, the encyclopedias, you'd have like 20 volumes, right? Alphabetically. Yeah, I would do the same. Exactly.
yeah, yeah. So there's no internet, no Google search, but so I spent a lot of time reading that. But as I graduated high school and I went to college for 2 years, and then I joined the military, and I went into I was still very interested in technology, and I went into I was a submariner. I was on a nuclear power fast attack submarine. I spent 6 years in the Navy, and I came out. I spent 2 years of that going to basically it was right when the Navy was converting over to all digital electronics, and so I spent a lot of time at called the Naval Underwater Systems Center, going through a lot of training on digital electronics. And so I came out of the Navy, and I got a job working in the defense industry in Albuquerque, and I was going to school at night. And I was working at a defense contractor here, and Intel had built the factory in Rio Rancho, and I lived not too far from it. And at one point, I remember we were actually doing layoffs at the defense contractor I worked for, and I was working as a manager at the time, and I was still going to school. And I remember talking to Intel HR, and they mentioned, "Hey, we're hiring," and they said, "So if you guys have resumes, send them over." And so I actually put my resume in, and I ended up getting hired, and that was in 1992. And so that's how I come into to Intel at the time. I finished school, and
What was that, an engineering degree or what was that?
no, I had a Bachelor of Science degree, and that was a business degree. And that's so long ago, I don't even hardly remember. But yeah, I kind of went to just third tier school, not anything fancy. But I was always interested in technology, and I always had a really good grasp of math and basically science overall. And I've termed myself as a lifelong learner, and so Intel was, especially the early days of Intel when I came in, it was a rich environment for learning. There was just so many good things. That was a great company, still is a great company. I don't keep too close to it nowadays, but I think that they really provided a lot of training, and you could do about anything you wanted to do within the company if you showed the motivation and the aptitude to do it and stuff. They were very, and it was certainly a blessing for me in my career to be able to get the jobs that I had and be able to do things like that.
Yeah. Yeah, no, that's the fantastic story. Well, listen, thank you so much for sharing that. As I mentioned, it's a little bit older technology. Semiconductor still, it's one of the most complex processes in the world. And the concepts just apply no matter how many steps you have. Thanks again, Zane. Much appreciated. The audience, I'm sure, will love it. And let's keep in touch.
Very good. Ed, thank you. It was a pleasure talking to you.
Enjoyed it. Bye-bye.
The Operation Science podcast requires more than a conversation. It takes action, research, and collective wisdom. If today's episode resonated with you, we'd love to hear your insights. Join the conversation and help us shape the future together. Join the Operation Science Institute at opscience.org. We'll be back with more stories, strategies, and real-world solutions that are making a difference for everyone. In the meantime, be sure to subscribe, rate, write a review, and share it with someone you think would benefit from it too. Thanks for listening, and see you on the next episode. The views expressed by our guests are their own and do not represent their company's views unless specifically stated as such.